interpreting hazard ratio. So how do you interpret your hazard ratios? So hazard ratio is just the ratio of the hazards between two groups for unit change in a continuous variable. So if your analysis gives you the coefficients, then you exponentiate the coefficients to get your hazard ratio. So the hazard ratio is usually the ratio of hazard between two groups for unit change in a continuous variable. So in terms of sex, male to female, in terms of age, maybe a lower age to a higher age. So that's just what the hazard ratio means. We're usually comparing a particular level of a category. So hazard ratio is equals to 1. It means there is no difference in hazard. When it's greater than 1, it means there's increased hazard, worse outcome. When it's less than 1 compared to it means that there's a decreased hazard, better outcome. So the hazard ratio, example of hazard ratio, 2.0, it is twice the hazard. 0.5 is half the hazard. 1.5 is 50% increase in the hazard. And 0.75 means 25% decrease in hazard. So converting between representations, so when your hazard ratio is usually the exponential of your coefficients. If you want to convert your HR to, that's the hazard ratio to coefficient, you take the natural log of your hazard ratio. And also for percentage change, you just subtract 1 from the hazard ratio and multiply it by 100 to get the percentage change in hazard, which can either be an increase or a decrease. So example, for a binary predictor, you can see the Cox output can give us a coefficient of minus 0.47 and a standard error of 0.15. So the exponential of that minus 0.47 will give us the hazard ratio, which is 0.625, with a confidence interval of 0.47 and 0.84. So what this means is that that particular new treatment reduces the hazard of the outcome by 37.5% compared to the standard care. So this is what this particular hazard ratio is trying to mean, because we have already subtracted 0.625 from 1 and we get 0.075. So that means that it's 37.5% decrease in that part. People that are experiencing the treatment to get in terms of dying compared to those that have the standard care. You can also put it like this too also. We can say the hazard ratio, then the hazard ratio means that those that are receiving the new treatment are 0.625 less likely to die compared to those that are receiving the standard care. It's also another way of interpreting it. And that's a continuous predictor. You can see now we have a coefficient of 0.03. If we take the exponential, we have 1.03. And also if we check that of 10 years, we are going to say exponential of 0.03 times 10. Don't forget that in our Cox regression model, we have x with each of its coefficients. So we're going to put the value of 10 here. What you can see here is that the hazard ratio of those in 10 years is more than those at the lower year. So how do we interpret this? It means that each additional year of age increases the hazard ratio by 3%. So 1.03 minus 1, we have 3, 0.03. And if you convert it to percentage, that is 3%. So it means that for each particular year, the hazard of experiencing that mortality, it increases by 1.03. Or you can say it increases by 3%. And also in 10 years' time, the hazard ratio is going to increase by 35%. So confidence intervals for hazard ratio, how do you explain it? So the confidence interval is usually, if it includes 1, if you see in the confidence interval there is going to be 1 in it. For example, if you look at this confidence interval, there is no 1 in it, so which means it's significant. But if you see something like 0.47 to 1.6, 1 is included in the confidence interval, it means that that particular hazard ratio is not statistically significant. So the p-values and the confidence interval. So we test for the H0, the hazard ratio is usually 1, and usually dichotomous, significant or not, but doesn't show magnitude or precision. Unlike the confidence interval, which shows the range of possible values of the hazard ratio, it also indicates precision and also shows clinical significance. So the confidence interval is usually preferred for interpretation. So what are the common misinterpretations of hazard ratios? HR is equals to 2 means you die twice as fast. No, this is false. It means double the instantaneous risks. The hazard ratio is 0.5. When you say means 50% will survive, this is also wrong, because hazard ratio is usually about rates and not proportions. When you also say the HR constant means same absolute benefit, this is also false, because absolute benefit depends usually on the baseline risks. And when you also say non-significant means no effect, this is also wrong, because it could be due to small sample sizes. So hazard ratio versus risk ratio, what's the difference? Hazard ratio compares instantaneous event rates and usually from survival analysis and accounts for timing, while risk ratio compares cumulative probabilities and usually from standard analysis and does not account for timing. So these are the major differences. Unlike hazard ratio, which accounts for timing and is usually used in survival analysis, risk ratio is usually used in standard analysis and doesn't usually account for timing. So hazard ratio and risk ratio are often similar, but they are not actually the same. So for unadjusted hazard ratio, we have a single predictor model and can maybe confounded and also simple interpretation. But for adjusted hazard ratio, we have multiple predictor model which controls for confounders, independence effect, and also preferred for causal inference. So this is different between the unadjusted and the adjusted hazard ratio. For usually for the unadjusted hazard ratio, you usually use a single predictor model and can actually be confounded and just a simple interpretation. But adjusted hazard ratio usually accounts for other covariates inside that particular model. So and it controls for confounders and usually preferred for causal inference and also independent effects. Clinical versus statistical significance. In terms of statistical significance, we usually base it on the p-value or the confidence interval, and also it depends on the sample size or also the mathematical concept. But clinical significance is more or less like what's that particular variable, does that, even though it is statistical significant, does it have any effect on the hazard ratio in real life or the outcome in real life, and also is usually based on the magnitude of the hazard ratio and also considered context too. So an example now, we can have an hazard ratio of 0.95 and a p-value of 0.901. So you can see that this is statistical significant, but it is what's clinically trivial because we have a 5% reduction in that particular hazard. So the 0.95 is almost close to 1. So even though it is statistical significant, in terms of hazard, you can see that the hazard is less because the hazard is just less than 0.95 compared to the reference value. So the number needed to treat. So unlike odds ratio, you cannot easily calculate the number needed to treat from hazard ratio alone because the hazard ratio is usually a relative measure and the number needed to treat is absolute and time dependent, and it also needs baseline risks and time horizon. So how do you calculate your number needed to treat? You calculate the number needed to treat from the survival course at specific time. So the number needed to treat is actually the average number of patients who need to receive a treatment for one additional patient to benefit compared with a particular control, maybe usually the standard care or the placebo. So anytime you have a lower number needed to treat, it means that the treatment is more effective. If you have a higher number needed to treat, it means that the treatment is less effective. So for example, now a drug reduces the risk of heart attack from 10% to 5%. That is, the hazard ratio is going to be, let's say, for example, now 0.95 or 0.90. So it means that the number needed to treat is going to become 1 divided by and that particular hazard ratio, which can be 0.95. So when you take 1 divided by 0.95 now, so if the hazard ratio is 0.95, you can see that now that it's just a 5% reduction in that particular risk of dying. So which means it's 0.05. So you just say 1 divided by 0.05. So when you say 1 divided by 0.05 now, you get 20, which is the number of people that you are needed to treat to prevent one heart attack. So this is what we mean by number needed to treat. How many people do we treat to prevent one person from experiencing that particular outcome? So we have effect modification also in terms of hazard ratio, just like we did in the regression, which is the treatment. You can say, for example, treatment interacting with gender. So the hazard ratio can be 0.6 in women, and you can see for women it's likely for the hazard ratio to increase, which means that considering the treatment with gender, whereby I can see gender now is now the interaction effect. It's now the interaction term because the hazard ratio increases by each level of the gender. So in terms of the treatment for men, the hazard ratio would be 0.6. But when you now consider women, you see that the hazard ratio has increased to 0.85. Which means that the difference of experiencing between treatment A and B, the difference is going to be, for men is going to be 0.4, while for women is going to be 0.15. So when you are reporting it, you usually report your main effect alone. Can be misleading. So when you report your main effects alone, it can be misleading. Try to consider the interaction, so that your report is going to show that based on this particular variable as the interaction variable, or the effect modifier, this particular effect of the treatment increases. Also, you report your hazard ratio for each subgroup and you test statistical significance of interaction. So reporting hazard ratio we have the point estimate. Your good report should include your point estimate, your hazard ratio, your 95% confidence interval, and also your p-value, your reference category for categorical variables, and also your adjustment variables if multivariable. Also your sample size and number of events and the interpretation in context. So this is what a good reporting includes. So this is an example now. The effect of drug X on mortality in heart failure. So treatment with drug X was associated with a reduced mortality compared to the placebo. If you have an adjusted ratio of 0.68, it means that that treatment with drug X is have an hazard ratio of 0.68. So those that take drug X have a lower risk of dying of 0.68 compared to those that took the placebo. You can also see that the hazard of those that took drug X is 32% lower than those that took the placebo, any way that you choose to interpret it. So the confidence interval is 0.53 to 0.87, and the p-value is usually 1.002 after adjusting for age, sex, and disease severity. So among 500 patients, we have 250 per group. 180 deaths occurred during a median follow-up of 36 months, which usually represent a 32 reduction in the hazard of death. So visualizing hazard ratio, we have the forest plot. It displays multiple HRs with confidence intervals. The vertical line at HR is equals to 1, and the points to left favor intervention, points to right favor control, usually useful for meta-analysis or subgroup analysis. So the tips: usually use your log scale for HR axis, include your sample sizes, and also you try to order your effects, order by effect size or clinical logic. So usually use your log scale for HR axis and also include sample sizes when you try to visualize your hazard ratios and other effect size or clinical logic. So this is an example of a hazard ratio plot, forest plot. That's actually so this is an hazard example of you have the hazard ratios. This is a forest plot that was developed in R. So you can see the number of events. We have our grouper p-value, we have our log rank, we have our hazard ratios, we have the baseline. You can see all the informations. We have our covariates. Everything is already available and it's very easy to see. So we're going to be discussing more on how you can apply all what I've talked about in the lab.